Hi, my name is Bianca Lopez Parniti, and this is my presentation on Lab 3, Black Holes and Orbits. So this lab was broken up into two sections. The first part, the purpose was to code and use a unique star trajectory to find the unknown mass of a black hole. And for the second part, it was to create a figure-8 orbit around both a planet and a moon inside the same previous system as before. So the two main physics principles used in this lab were forces and centripetal kinematics. This entire lab was based around orbiting in space. So obviously the main force here was gravitational forces around the system to keep everything moving in an orbit. And then the forces were all broken down into components, both the parallel and perpendicular due to the circular motion of the orbit. And so some relevant equations. The first one dealt with momentum. Change in momentum is equal to mass times change in velocity, the net force being the derivative of momentum, the formula for gravitational force, and then velocity update formula. So as a preview of the results, this is the final picture kind of drawn out by both parts of the code. For the first part, we have the mass of the black hole that we calculated in the code itself, which I will show briefly. And then the second part is the orbital speed to keep the spaceship orbiting around the planet and the moon, which I also will explain shortly. So the system and surroundings. For part 1, the system was the star and surroundings was the black hole. And for part 2, the system was the spaceship and the surroundings were the planet and the moon. And so here are the initial conditions for both parts. I'll also talk over them again when I show the code. But we have the star mass, the black hole mass, which is what we're solving for, the initial momentum of the star, the time and the time step. And then for part 2, we're solving for the initial velocity of the spaceship, the planet mass, the moon mass, the spaceship or the starship mass, and then the different times. Okay, so on to the code for part 1 of the lab. So this is just all the setup. It's the code to really set up everything in the lab. And here's the important part. It's all the calculations. As you can see, you have the velocity update, the momentum update, how it's broken up into the perpendicular and parallel components, and then finally how everything is summed up to find the mass of the black hole, and then we print it at the end. So this is the results for part 1 of the lab. It's just the mass of the black hole at different time steps as it goes around in orbit. And so once again, this is part 2 of the setup. You have everything just really setting up the second part of the code. And here are the calculations. We just found the forces of everything in the system, such as the ship on the moon, the planet on the moon, and then the moon on the ship, and then the planet on the ship. And then we use Newton's second law and the position update formula to make sure everything was moving correctly. And then at the end, we just plugged in different speeds to try to get it moving in an orbit. And this was the successful speed for both the x and y direction, 2.5 e to the 4 meters per second. So some similarities is that the mass of the black hole found in the model is comparable to in real life, since it was around 9e33 kilograms in mass, and the spaceship was able to successfully orbit the planet in a figure-8 configuration. But the only difference is that obviously the code is too simplistic to actually model behavior in real life. So some possible sources of error are always glitching on GlowScript because I'm using a MacBook, always quoting errors because I'm not a computer scientist, and also different trials giving different outputs, so that creates variation. So the first additional question essentially asks the difference between rate of change of momentum and net force, and I said that net force is the sum of all the forces, so it describes more of how the combination of all the external forces influence the motion of a particular object. So it's more like looking at the cause of the motion. And then on the other hand, the rate of momentum, the change of momentum, it's the rate at which the momentum is changing, which describes more of like the actual change in both curvature and also the size of momentum. So both parallel and perpendicular components due to the forces. so due to the net forces. And for the final question, it asked what additional forces we would need to, or what additional interactions we would need to include in the computational model if we increase the system size. And I said we would need to add all the additional forces due to the black hole on the rest of the system, since it's not in the current code. And then the most dominant interactions would always be between the most massive objects. That is all. Thank you for listening.